I think she's. I don't.
I can text her in your chat and say, Sarah, are you on?
I think it's. I'm not. She'll be back. Let's begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for your students. Just ask you to bless this class today, Lord. In your name I pray. Amen. All right. So we have finite fields. Section 14.3 is on finite fields, and it's really quite beautiful what you can say about Galois theory for finite fields. Let me just rattle off the first paragraph here. He says a finite field F, right, has characteristic F equals to P for some prime P, right? And so that says that F is a vector space over Fp, by the way. So it's a finite field, right? And so, I mean, in other words, we could say that the degree of F over the finite, F sub P as we call it, is equal to n, right? He says then the field has precisely P to the n elements. And we've already seen, following proposition 13.37 from chapter 13, of course, that as F is isomorphic to the splitting field. So F is isomorphic to splitting field of what? X to the P to the n minus x. All right. And anyway, we're going to denote this by. So we're going to just denote this by. He says this is going to be F sub P to the n. That's going to be the splitting field of that particular polynomial. All right. So if you wonder what F sub P to the n is, that's his notation for the splitting field of the polynomial x to the P to the n minus x. All right. He says, okay, well, the field F to the P to the n is Galois over Fp, with cyclic Galois group of order n generated by the Frobenius automorphism. He says that the Galois group of F to the P to the n over Fp rather, is generated by the Frobenius automorphism that we talked about before, and so it's isomorphic to Z mod NZ. In particular, sigma P is a mapping from the splitting field to the splitting field governed by sigma P of alpha equal to alpha to the P. All right. So he says every subfield of the splitting field would then correspond to a subgroup of Z mod NZ. Hence, for every divisor D of n, there is precisely one subfield of the splitting field of degree D over Fp. And it's the fixed field of the subgroup generated by. So what are the subgroups of? What are the subgroups of this? Like, what's a subgroup? H a subgroup of this thing. What's it look like? Something like sigma P to the D, right? Where D is the divisor of n, right? So, I mean, if D happens to be relatively prime to n, then I guess it's just the whole Galois group again. But if D is not a divisor of n, then it's an honest to goodness subgroup. D equals to n, it's the identity. Hey, I'm not writing in, you need to get some glasses.
Covered context, but it's sigma p to the what?
Sigma p, bidibidibidibidoo. So many sigmas.
Oh, the very bottom.
Oh, to the D.
Signal p to the left.
Langle, yeah. Linear was, I was langle-wrangling in linear. They're like, what are you saying? What are you saying? So I had to explain it.
Did you say if d was relatively prime to something?
If D is relatively prime to n, then that would mean that it's also a generator for the whole Galois group. All right. Let's see here. He says, he says the Galois group of f p to the d over fp is generated by the image of, I don't really know if I need to get in the weeds so much here. I'm not sure I'm going to really do anything with this. I'm sorry, guys. Image of sigma p in the quotient. I'm anxious to get some numbers here. This is, let's see here, gal. He says we can recover the Frobenius automorphism for the extension fp to the d over fp. He says, note, however, that sigma p has order n in the full Galois group, but it has order d in this. All right. Anyway, let's then get to the point here. Proposition 15, it says that any finite field is isomorphic to f p to the n for some prime p and some integer n. And again, fp to the n is the splitting field. Just to remind you, fp to the n is splitting field for x to the p to the n minus x over fp. And it has a cyclic Galois group of order n generated by the Frobenius automorphism. The subfields of fp to the n are all Galois over fp and are one-to-one correspondence with the divisors d of n. They are the fields fp to the d. Well, I've said most of this, but I'll just say dot, 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 dot. Subfields of fp to the n are fp to the d, where d is a divisor of n, and indeed fp to the d are fixed fields of sigma p to the d. I mean, it's just so greedy. You can say so much about so many different things all at once, in contrast to all of the work we had to do to like just discover the substructure just of like x cubed minus 2 in our previous work. I mean, this is amazing how much that we're able to say here just like that. I'll look at corollary 16. This is a kind of neat calculation. He says the irreducible polynomial x to the fourth plus 1, of course that's in the integers, polynomials with integer coefficients, is reducible modulo every prime p. And so his argument is to, well, what does he mean reduce mod p, right? So he says, look at x to the fourth plus 1 over fpx, right? And first of all, what happens if p equals to 2? If you tilt your head and squint, you can see that you've got x to the fourth plus 2x squared plus 1, am I right? 2 is 0. So that's x squared plus 1 squared reduced. All right. And then he says, otherwise, p is odd, right? And he points out something that you students of number theory are doubtless aware of, that p squared minus 1 is divisible by 8. He says since p is congruent mod 8 to either 1, 3, 5, or 7, and all of these square to 1 mod 8. Anyway, you can try. P squared minus 1 is always divisible by 8 for an odd prime p. And so, hence, x to the p squared minus 1 is divisible by x to the 8th minus 1. Does that make sense? What would it mean for p squared minus 1 to be divisible by 8? So like, let's think about that for just a second here. P squared minus 1 would be equal to 8 times some j, right? So if I had x to the p squared minus 1, that would be x to the 8j minus 1. And he's saying that this is divisible by x to the 8th minus 1. Does that seem right? Of course, we are working mod prime p, so I may be forgetting something about the particular quirks of working mod, in characteristic p, right? There's some really greedy polynomial identities that are true there that I may need to exploit to see this. I don't know. So I'll be honest, I don't immediately see this, all right? But I'm content to believe that this is something you can work out, or it's something that we should all see immediately already. But you guys are tired. Anyway, this is neat. So x to the 4th plus 1 divides x to the 8th minus 1 divides x to the p squared minus 1 divides x to the p squared minus x. So what is that? He says, this shows that all the roots of x to the fourth plus 1 are also roots of x to the p squared minus x, right? Think about it. I mean, if we have a root of x to the fourth plus 1, it must also be a root of x to the p squared minus x. He says, since the roots of x to the p squared minus x are the field f sub p squared, it follows that the extension generated by any root of x to the fourth plus 1 is at most degree 2 over fp, which means that x to the fourth plus 1 cannot be irreducible. Ooh, that last sentence is kind of a doozy. Since the roots of x to the p squared minus x are the field pf squared, it follows that the extension generated by any root of x to the fourth plus 1 is at most degree 2 over fp. This is a rather sneaky paragraph, but it really says something kind of neat, because I don't know if you remember or not, but proving x to the fourth plus 1 was irreducible, was reducible mod every prime p was a rather unpleasant homework problem in abstract algebra 1, which I don't know if I even assigned to you guys because I got lazy this year. Did I assign that? When I first did this, it took me like, I don't know, it took me like 4 hours to figure this problem out, like all of it. It's got a lot to it if you don't have tools to use. All right, anyway, I wanted to get to the point here, which is I love Proposition 18. I want to share with you Proposition 18 because it's just so neat. And this, honestly, this is a little bit of a detour from Galois theory for us, because I'm not really going to do much with finite fields in here except to just say the words I'm saying today. And I'm sure I've assigned you a homework problem. If you have a love of finite fields and you'd like to do more homework problems of finite fields, you're welcome to do that. You know, that's a freedom you have.
For extra credit?
Yeah, for extra credit. And sure. In fact, reverse extra credit, as in, like, if you do problems in finite fields, I will take points away from Liam. The problem.
So you'll take points from Liam and give them to me?
Yeah.
Oh, Liam, you're going to be so taken aback by how many problems I do.
So, Liam, you better buckle down, because if they work hard, you're going to need to work harder. See here.
0 points at the end, and we'll all have 1,500.
So here's the beautiful thing, which is argumented. Yeah, listen to me. Argued is that xp to the n minus x is precisely the product It is the product of the distinct irreducible polynomials in Fp of x of degree d, where d runs through the divisors of n. All right, so like this is best illustrated by example. I mean, you guys remember how much? Maybe you do, maybe you don't. But like determining and cataloging irreducible quadratics or cubics over a finite field is really important for the problem of deciding whether or not a given polynomial is irreducible. Even if we do like the reduction, if we take a polynomial over the integers and then reduce mod p, it still comes back to the question of, can you find a reduction mod p, right? And so knowing what are the irreducibles of a given order is very useful, because then you can divide by them to see if they're there or not. And if they're not there, then you can safely assume that there has to be a larger irreducible or something. I mean, it's important to know what they are, because we can't just evaluate and see if there's 0 for quartic or higher. Saying just something to keep in mind. Anyway, so he says about irreducible quadratics over f2. So we're supposed to look at what? We're supposed to look at x to the 2 squared minus x, otherwise known as x to the 4 minus x. That's supposed to be the product of the distinct irreducible polynomials in fp of degree d, where d runs over.
How did you know that n was 2? Oh, quadratics.
Yeah. So irreducible polynomials, product is distinct irreducible polynomials of degree d, where d runs over divisors of what? Of I think runs over divisors of n. What's n here? Oh, n is 2. What are the divisors of 2? 1 and 2, right? So we're either looking at degree 1 or degree, let's see here. So this is what? So what he does is he says, okay, so what I'm going to look at is x to the 4th minus x, and I'll divide by the uninteresting ones, namely x and x minus 1. See, that, I mean, of course, x minus 1 is the irreducible polynomial of, well, excuse me, x and x minus 1 are the irreducible polynomials of degree 1, right? Linear polynomials are irreducible, right? You can't factor them further. And so what does that give you? Right? And that is the irreducible, the unique irreducible quadratic over f2. Which you can easily check by plugging in 0 and 1 and seeing that they both give you 1, which is not 0. And since this is a quadratic, we can check irreducibility by plugging in zeros. Sorry, eventually that will not be funny to me, but it hasn't stopped yet. Now, are these dead? Oh yeah, these are dead. Ooh, kind of proud of that one. Let's see here. All right, so next up. He says, how about the cubics over f2, irreducible cubics. So we do x to the 2 to the 3 minus x, which is x to the 8th minus x, right? And if we want to get the cubics, we got to get rid of the noise. What's the noise? Well, you still got your x. You still got your x minus 1. And what are divisors of n equals to 3 here, right? 1 and 3, right? So this doesn't come into play. It's not. I mean, if we were looking at the 6th power, then we'd have to divide off the quadratic, the linears, and the cubics before we could find irreducible order 6 things. Yeah. But that's all she wrote here. And so of course that's, x to the 7th minus 1 over x minus 1, which is obviously x to the 6th plus x to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1? Yeah, plus 1. And he says, well, it's easy enough to see. Okay, he doesn't say that, but here they are. That factors into x cubed plus x plus 1. And x cubed plus x squared plus 1. Yep.
So why do you not have to divide by 3? Because it's where d is the divisors of n. But why does 3 not matter?
Oh, 3 does matter, but what's ever left over has to be the order 3 ones. Because this x to the 8th minus x has got to be the product of the linear irreducibles and the cubic irreducibles. That's the theorem. Because 3 has divisors 1 and n. And if you multiply this out, you get back up to here because 2 equals to 0 at the moment. And by the way, those are the 2 possible irreducible cubics over F2. The cool thing about this is once you find out that this has order 6, it shows you that there are only 2 irreducible cubics over F2. Which I think before in the abstract, like, is that obvious that there should only be 2? I don't think it's obvious. And this just gets more profound as you go up in order. Yeah. So this is pretty neat. I mean, it gives you a way of generating irreducible polynomials of a given degree over a finite field. It's pretty neat. Completely divorced from things we've said before, really. And then he actually, so like on page 588, he goes on to explain a strategy for counting how many irreducibles there are of a particular order using something called the Mobius mu function. But I'll let Dr. Smith tell you about that. Yeah.
Is there any way that we would be able to figure out how he managed to split up the larger polynomial into the 2 cubics? I mean, like, is there a strategy that he approached for that?
Well, I can tell you, here's what my strategy would be. I'd start with x cubed, and then I'd say, well, that alone's not going to work because it's reducible. And then I would add x to it, and I would say, well, that alone's not going to work because x factors out. And then I would add 1, and I would go, maybe that works. And then I would plug in 0, and I would get 0 plus 1, which is 1. And I would plug in 1, and I get 1 plus 1 plus 1, which is 1. I go, aha!
So then we know that has to factor.
Yeah. Fortunately, we're not at 4th order, because then the answer to your question would be more complicated. It's not for free. It's just a tool.
You can't test the zeros in the quartic, am I right?
That's right. See? Now everybody's starting to get the joke. That's good. It's a joke. Oh. I like you guys. Let's see here. So he makes this really, this cool, what was the algebraic closure? What's the algebraic closure of the finite field characteristic? F sub p, right? Z mod pz up to isomorphism. What's the algebraic closure of that? What's that mean? That's supposed to be the field in which every possible polynomial with coefficients from Fp does what? Splits, right? So if you start thinking about that, that just means that you need to have zeros for all possible irreducible factors to polynomials of different order, right? And so it's not hard to see that a reasonable construction of the algebraic closure of Fp would be the union n greater than or equal to 1 of these splitting fields of f sub p n, fp to the n. So because this builds at order by order all possible irreducible factors, right? It's giving you everything you need to build zeros of arbitrary polynomials of arbitrary order, which means that this can function as the splitting field of an arbitrary polynomial with coefficients in ZP. So that's kind of neat, a side effect of this section. All right, move on here. I really don't have anything to say about section 4.4, hardly at all, except that maybe it would be good to read it. I would encourage you to read it. The ultimate result of section 14.4 is section 14.4 really culminates with the theorem 25, which is pretty cool. It says that if K over F is finite and separable, then K over F is simple. What's that mean, simple? Yeah, it means K can be written as F adjoin alpha for some particular element alpha. Yeah. Now that brings us to section 14.5, which is another neat example. This time, characteristic 0. So since you guys made me start 10 minutes late, I get to go 10 minutes over, right? Ooh, a meeting with SGA. Ooh.
It's for math club, so it's very important. It's for the shirts that we talked about before. You canceled on me, so it's not even my fault.
SGA. Whatever. Fine. Let me skip straight to the example then. So here it is. Q adjoin the fifth root of unity is Galois over Q. Yeah, this is from section 14.5. So section 14.5, what he said before this, fine, theorem is this, that the Galois group of Q adjoin the nth root of unity is isomorphic to the multiplicative group. Well, I would call it UN. All right, so the group of units mod n. So the order of gal Q zeta n over Q, of course, is equal to Euler phi function of n, et cetera, et cetera. And in fact, the typical automorphism, sigma a, of zeta n, you can just define to be zeta n to the a power. And that also, that is the, gives you a window into the isomorphism to un. You take anything in un and raise it to that power, then that's giving us an automorphism of Q adjoin the nth root of unity. So like sample, I don't know why I'm doing this, I don't have time to do this, but here we go. Zeta n, real question is why did I do what I just did over there? If I was smarter, I wouldn't have. But anyway, that ship has sailed. So sigma a of that is, of course, this is essentially explaining the isomorphism between the automorphisms of the Galois, the automorphisms forming the Galois group in Zn. If you give me one of them, you can generate the rest of them by taking un powers of them I guess the question is, how do you define the first automorphism of the Galois group here? I want to focus our attention on this example here. So Q adjoin the fifth root of unity, he says is Galois, it's a Galois extension over Q with Galois group essentially isomorphic to Z mod 4Z. So the Galois group I'm going to call this thing K. He claims we'll have the form 1 equal to sigma 1, sigma 2, sigma 3, and sigma 4. All right. He says a generator for this cyclic group is what? Now, I don't think all of these things are obvious from this section. He's building off what we've done with the splitting field for First of all, it's a the Q adjoin the nth root of unity, right? It is the splitting field for the cyclotomic polynomial of order n, is it not? Which means that it's a Galois extension over Q, because that was one of our 4 equivalent characterizations of a Galois extension, right? Splitting field of a polynomial. This is that, therefore it's Galois. To prove that the Galois group is cyclic, that just goes back into the substructure of cyclotomic fields, right? Which is very special because they're built from this, nth root of unity and its powers, which satisfies very particular relations. But he points out in particular here that, if we're looking, so we have reasons to understand that its Galois group is order 4 and it's cyclic, and he points out that a generator is sigma 2, and he's defining sigma 2 here, okay? He says let sigma 2 of the fifth root of unity equal to the fifth root of unity squared. Then extend. So if I defined that function on the generator of K, that uniquely defines the automorphism sigma 2 on all of K, right? Do you guys agree with me? Do you know what I'm saying? I'm saying that this suffices to define sigma 2 an element of aught K, since K is Q adjoin the fifth root of unity. Like if I tell you what sigma 2 does to that, I've told you what sigma 2 does to everything. And in addition, he points out that this is enough to generate the Galois. This is going to be a generator for the Galois group because what's sigma 2 squared? That gives us this, right? And what's sigma 2 cubed? If you work it out, we've got so I let sigma 2 squared, that takes me to the zeta the fifth root to the fourth power. Then what does it say? You're supposed to do sigma 2 of zeta. So it's a homomorphism, right? So I got this, which is to the what? Sorry, my zetas are unstable. It's just a fact. But we still haven't gotten back to where we started yet, have we? But then when you look at sigma squared, the fourth iteration, so that would be oh yes, this would also be, thank you. Very good. Because zeta to the fifth is equal to the identity again. Now this would be, of course, did I do something wrong? Oh, I'm an idiot. What? Son of a gun. Oh. You say to the what? What does this work out to?
So that's
How did you?
that's zeta 5 to the 8th squared, which is zeta 5 to the 6th, which is equal to zeta.
So I don't have any errors here?
Could you just do like sigma 2 of sigma 2 cubed? So like it would just end up being sigma 2 of zeta cubed because we got that on the line above. That would be 2 to 6, and then it would just be zeta.
I'm not saying it's not a lot. I have, there's something wrong. I'm thinking I can't put my finger on it. What'd you say? So the sigma what?
Sigma 2,
Uh-huh.
and then sigma 2 cubed, which we got above, was just zeta cubed.
Which then,
That's just that square.
oh, I'm an idiot. So that's sigma, that's to the 6th power, which is that again. Okay, I'm an idiot. So finally we have found a power that when we act with the power of the automorphism on the generator, we get back just the generator again. But if it fixes the generator, and by assumption it fixes 1, it's fixed the whole field. In other words, sigma squared to the 4th is equal to 1 again. And that's why we could say that this Galois group is just generated by sigma 2. All right. Now, of course, at this point, we have an important SGA meeting to go to. But I will just tell you, we'll pick back. I'll finish this example and start next class. But what I'm going to show you is that there is, of course, it's a cyclic group of Z4. There's one subgroup of order 2, and then that means that there's a corresponding fixed field for that subgroup. But it's not at all obvious what the fixed subfield is here of this cyclotomic extension. Like I think it actually is kind of like not at all obvious what the fixed subfield is. And I have good evidence to back the fact up that this is not obvious because I have given this as a test question before, and I find that students found this non-obvious. So I have objective evidence on that point. Finally, this section ends with a really interesting question, which is a given finite group a Galois group of some polynomial? It turns the tables, like given a finite group, can you find a polynomial for which that finite group appears as the Galois group of that polynomial? So that's where I'll finish that discussion next time, and then we'll go on to section, I think 14.7 on solvable and radical extensions, all right? Thanks, guys. See you Friday.